Hi guys, I'm intending to give a duplicate presentation that I gave yesterday on account of the fact that Big Blue Button didn't actually show all the details I had on slides in the presentation. So here we go. Um, Uniform delay hardware pipelines. Uh, what what's going on here is that each of these rectangular blocks represents specialized processing of data. Um, so trivially, it might involve performing the square root of a number and then raising that number to the power of 10 in the second stage, hardware stage. And in the third stage, it's doing something else. And by the time the, the process data is received at the final stage, its output giving the total result. And the key idea here then is data is fed into this pipeline and it comes out with a result. And five different levels of processing are given to the data. In other circumstances, we might have 10 hardware stages to produce a final result, or just two stages to produce the final result. And notice that we have a clock line. It's a clock line here representing digital 1, digital constant digital 1, then goes down to digital 0, and then digital 0. And the idea is that the clock period is from the rising edge to the next rising edge. That's called the period of the clock, and we might have 50,000 cycles occurring every particular second, or we might just have one cycle per second. Um, so in order to understand the operation of a uniform delay hardware pipeline, firstly, we need to consider that a successful pipeline will involve processing in stage number 1, taking more or less exactly the same time that processing in stage 2 takes, and similarly with stage 3 and stage 4 and stage 5. So it's a uniform delay. That explains the uniform delay part of the description of the hardware pipeline that we're looking at the moment. What, you might be wondering what these vertical lines represent, given that there's a clock line feeding this clock signal to each component at the same time. Well, the operation is to be explained as follows. The rising edge of the clock, in other words, the rising edge of the clock, when it occurs at this latch or memory element, will allow data from this processing element to be temporarily buffered or temporarily captured at this point, allowing this hardware unit to input it. At the same time that the rising edge appears at this memory element, it's also um, arriving at this memory element, which in turn allows data that's just been processed by hardware element number 2 to be temporarily captured and made available to this hardware element number 3, and so on. The assumption, therefore, is that the clock cycle, rising edge to rising edge, is that length of time is sufficient to allow each and every one of these 5 different elements time to complete processing. I mean, think of it in these terms. If processing in element 1 takes a minute, but the clock comes in after just 58 seconds, then the processing hasn't been completed, and it needs to be completed in order for the pipeline to operate successfully. Um, Here's an illustration of the result of pipelining a computer system, and the pipeline is looks quite complicated, but the ALUs involved, and I guess what's actually happening in this particular pipeline is that uh, an, uh, an instruction is going to be fetched from data memory, and then it's going to be passed to a decode area, and then from the decode area it's going to go on to be executed and so on. So we learnt last term that even the simplest computer architectures involve this basic sequence of fetching an instruction, decoding it, and then executing it. And I'm sure this example architecture that you can see up in front of you is far more sophisticated than that. It's far more complicated than the one we looked at before. So the question might be arising um, in your minds: what on earth what benefit is obtained from pipelining an architecture? What's the big deal? Why are we doing it? Why should we invest time and design efforts into the creation of a pipeline? Well, I'm going to try and justify that in a few moments. First of all, what we're looking at are K-stage pipelines that have K different processing elements. And I'm assuming that each processing unit has a delay of Ti seconds. So between I equals 0 to I equals K minus 1, they all have roughly the same delay. And I'm assuming that the delay of our particular latch is T latch time. What I've just shown you is a typical hardware pipeline. And note the latches between the hardware stages, which I've mentioned already, and the presence of a clock. And if you're interested in finding out more, just Google Earl latch. And if you're operating with a 1 Hertz clock, in effect, you're looking at a period of 1 second, a cycle of 1 second. And if there are K processing units or hardware stages, this architecture is called a K-stage pipeline. And just to give you a little bit of intuition, what do you think ticks at 1.2 Hertz or 8 Hertz? Well, an answer to the first question is that your heart is probably ticking at that rate 1.2 times per second under fairly relaxed circumstances, I guess. It's also called a uniform stage pipeline because it's assumed that each hardware stage takes approximately the same time to process data. And in general terms, and this is quite an important consideration, if a complex task, whatever that task is, can be broken down into K equally hard stages of processing, and there is an implied order of doing the processing, then there is every chance, every possibility of pipelining the overall operation or task. And as we'll see soon, there is a lot of advantage in being able to pipeline the stages involved in producing completion of a particular task. If you're bothered by any of this, I mean, you can liken a pipeline to a factory assembly line. I mean, maybe building cars, and at the very first hardware stage, what's actually happening maybe is that you're taking a chassis and maybe you're attaching wheels to the chassis of the car. And in the second hardware stage, in the production of a motor car, you're actually maybe affixing transmission and the gearbox, and maybe in the next hardware stage, you actually um, embedding the motor engine into the chassis, fastening it, and so on. And the next hardware stage, maybe you're just putting internal furniture into the car. The next stage, maybe you're attaching the panels to the exterior of the car, and in the next stage, maybe you're filling all the particular reservoirs, like the oil reservoir, with suitable fluids and so on. And maybe the final hardware stage is when you're actually starting the engine and making sure that everything is going well. But you get the idea, and I guess the production of a motor car could involve maybe a 50 or 60 or 70 different stages, and not just a 4 or 5 stage pipeline. And again, you should be aware of the fact that what we're looking at is a parallel processing system. Why? Well, successive tasks can be streamed and the pipeline can be operated synchronously. So every tick of the clock, one of the hardware stages is going to be busy performing a particular task on the hardware or the data or whatever it is that you're dealing with. And think of it this way: if you put the first chassis into stage one at time 0, then at time 1 the chassis will have moved to stage 1, and you can now you can actually place a second chassis into stage 0. And as I said, if you've got 60 different stages, hardware stages, all dedicated to the production of motor cars, then maybe at any given instance of time, the pipeline is busy working on the production of 60 different motor cars. Anyway, I'm going to claim that the attractiveness of pipelining is that it's cheap and easy. And in fact, it's probably the cheapest and easiest way of constructing a parallel processing system. But it's a peculiar sort of parallelism that's being achieved. And you might want to, at this stage, consider some of the thoughts that we had earlier this term on the difference between a purely parallel system and a concurrent system, where concurrency is just the illusion of true parallelism. But anyway, we'll think about that maybe a bit later on. So one of the things that we should be considering is what is called speed up factors. Almost every CPU around will involve some hardware pipelining, and you might want to almost arbitrarily discover what pipelining is present on a Centrino processor. Just Google it and find out, what does it look like. How many pipeline stages are there as part of a particular Centrino processor? So the big claim now is that if a pipeline contains n stages, then in the ideal case we can expect a speed up of a factor of n. And I'm tempted to say, well, a pipeline can produce sort of like m different products n times faster than the case where you are actually building one thing, and when you finish building the first thing, you start building on the second, you start building the third one, and not until you finish the third you start on the fourth. So that you can expect a speed up of a factor event, and we'll look at that sort of more formally in a moment. So the advantages of using pipelining is is that basically a linear uniform delay hardware pipeline brings computational advantage over an equivalent non-pipelined system. And so let's just pause there. I mean, I'm talking about um, uh, solving problems or building things that has at least k different stages. So if you've got k different men, you could actually get those men to work on k different stages at the same time if you wanted to. If you've just got one man, then and you want to build k objects, or if I wanted to build k objects, then what I've got to do is to first of all um, complete each stage of building an object, and when I've finished doing that, I can start building the second object and the third object and the fourth object and the fifth object. And what I'm saying is that it's going to take me 5 times as long in those circumstances. So to make our understanding of pipelines a little more exact, we need some definitions. Precedence relationship holds between events or tasks A and B if and only if B cannot be done before A. So you can dream up all sorts of examples, like in cake making. You can't actually bake the cake until you've made all the mixes and the components. You've got the ingredients, all 10 different ingredients, and you've processed all the ingredients in the right way. And there's a certain um, in making a cake or making bread, you've got to, I think technically, I don't know very much about making cakes or making bread, but there are certain stages that you have to go through, like you have to prove the dough, you have to roll the dough, knead the dough, let it stand, and you can't rush things, and you can't do B before doing A, and so on. Or in gardening, I mean, if you're just simply sowing seeds, you've got to treat the soil in an appropriate way, sieve it, choose the right sort of soil or compost, uh, make sure that the temperature of sowing seeds is okay. You're not going to sow certain seeds in the middle of winter and so on and so on. Building a computer, yeah, you have to choose all the components and assemble them in a particular way, and maybe test things at every stage and so on. I mean, what I'm suggesting is that building a computer is a complex task, but you could break it down in principle into, say, 70 different specific tasks, which then could be pipelined or could be put onto an assembly line with big advantage, because you're going to be able to produce things faster and probably, due to economies of scale, um, far more inexpensively. So a precedence relationship R holds between subtasks S1 to Sk of a given task T if any of the tasks Si between 1 and K cannot begin until some earlier task under R completes. And have a bit of fun thinking about examples. And if S1 needs to be done before S2 and S2 before S3, we can talk about a linear precedence relationship, and we can represent it in this way, from left to right. S1 has to be done before S2, S3's got to be done before S4, and so on. And if you can do that, and in addition, each of the SI takes roughly the same length of time, And there's going to be every possibility of being able to pipeline um, the task, the series of tasks, and if you complete all the tasks, presumably you've uh, you've constructed an object or you've solved a problem or whatever. Um, in the general case, tasks cannot always be analysed into a linear precedence graph, but sometimes it doesn't really matter. It doesn't. Sometimes it doesn't really matter whether you do B before A or vice versa. But we'll see. So going back to our earlier observation, namely that to be pipelinable, all the tasks need to take roughly the same length of time. It follows that the pipeline clock period has got to be um, at least as great as the maximum of each delay taken by each stage and add it on to the time it takes to operate the memory element. I mean, if the clock period is smaller than Tor here, if Tor if the clock period is smaller than Tor as defined by this equation, uh, what this means is that you're not allowing a particular stage enough time to do its processing. Right, and so it should be obvious to you, from just by looking at the problem for a second or two. If the clock period is set too small with respect to the time it takes to process some subtask S cannot be processed to completion. So what I'm showing you here is what's called a space-time diagram. Space on the vertical axis, time on the horizontal axis. And in other words, I've got 3 stages, only 3 stages. I could have had 100 if the task had been very complicated. And I think it's I think I think it's Ludwig Wittgenstein who said actions and tasks and events are capable of infinite divisibility. So if you've got the smallest task, in principle, you could subdivide it as much as you wanted to do. So that's a thought to bear in mind. So what I'm doing here, what this diagram shows you, is task 1 in stage 1. So the superscript is the stage that this task is being processed by. The second stage is not doing anything, it's idle, it hasn't been given any work to do. And the third stage is again idle. Look what happens at time, the second period of time of operation of the pipeline. I'm putting in task 2 to be processed by stage 1, and that's happening at exactly the same time as the original task T1 is being processed by stage 2. And the third stage is idle. Okay, so looking at the next period of time, I'm not giving the pipeline any more work, I'm letting it be idle. But task 2 is now being processed by stage 2 of the pipeline, and T1 is being processed by stage 3. And the final column indicates that stage 1 and stage 2 are both idle. Stage 3 is busy. No, that's stage 3. Processing T2. It's completing task 2. It's completing work on task 2. So this is called a space-time diagram, and comes in quite useful a bit later on. So the 2 questions I'm going to ask you now, firstly, is how long does it take for a pipeline to execute n tasks? and that's supposing it has k stages. Secondly, how long does it take a simple non-pipelined processor to execute the same n tasks? And remember, the non-pipelined processor has got to perform k different things to get a result. So the answer to question 2 is that if the task involves k steps and each step takes tor units of time, then n tasks will take n times k times t units of time. I hope you can see that straight away. It's quite obvious. But the answer to question 1 might involve a little bit of thinking about. In the case of a pipeline, it takes k times tor units to process the very first task. I mean, if the first task has got to be processed by k different hardware stages, and each stage takes tor units of time, it's going to take k times tor units to process the first task. But after the first unit of time has finished, after you put in the first, after the first unit of time, we can simply put in another task into the pipeline, because if you think about it, at time 1, the first task is now about to move to stage 2, and logically I can put another task into the first hardware stage. And there are n-1 other tasks by hypothesis, and hence the total time is going to be k times tor plus k times n-1 times tor units of time. So think about that, and it should therefore take a total of k plus k times n-1 tor units of time to finish work on the n tasks. So I'm thinking about a k-stage pipeline. Each task takes k times tor units of time to finish. The first task takes k times tor units of time to finish. But then I've got n-1 further tasks, and each one of those is going to take n-1 times k times tor units of time. Definition of speed up. This is what I more or less started this presentation by talking about. There's some advantage. The speed up, so here's the definition. Definition of speed up. The ratio of time taken by a conventional processor to that taken by a pipeline processor is called the speed up of a k-stage pipeline, and it's given by the following expression. So it's the time, as we've seen, the time taken for a non-pipeline processor to process n tasks, which is n times k times tor, and divide it by the time taken by a pipeline processor or pipeline to process those n tasks, which is k plus n-1 times tor, which we've just seen. We've just seen that happen. Simplify that by cancelling the two tors, and we get nk divided by k plus n-1. So that's the speed up. And it doesn't take a lot of thought to see where n is very large. When n tends to infinity, the speed up of a k-stage pipeline is going to approach the number 1. Right? So what would happen? Okay, efficiency. I don't need to consider that. We've looked at this question already. What would happen if tor was less than max of all the times of individual uh, stages needed to process task T. Okay. So another definition is the efficiency of a k-stage pipeline. So I think I need to go back one slide. Um, uh, Speed up when n's very large. I think speed up is going to tend to k. You get a k. You think about this expression. Make n very large, then speed up is going to tend to k. But we'll come back to that in a moment. So the efficiency of a k-stage pipeline. Let's have a think about that. Talk about efficiency of machines. Our pipeline is no different. It's a machine, and we can talk about the efficiency. The efficiency eta of a pipeline is given by the ratio of busy time space spans to busy and idle space time times. So let's just hop back to our space time diagram. The efficiency of this pipeline is going to be measured by the ratio of busy time-space spans. Remember, this is a time-space span. It's busy. This is busy. That's busy. That's busy. That's busy. And I've got 1, 2, 3, 4, 5, 6 busy time-space spans. And I want to divide that by the total of all idle and all busy time-space spans. Well, I've got 3 idles here. That's 6. And the total of busy is 6, that's 12. So total of busy is 1, 2, 3, 4, 5, 6 divided by 12. So the answer is, according to the definition, it's 0.5. Okay? Efficiency is given by the ratio of busy time space spans to busy and idle space time spans. That's nk times t. That's the time. That's the total number of busy time space spans, and that's the time it takes to complete in terms of busy and idle space time spans. So eta reduces to n divided by k plus n minus 1. Think about that. Right, so if you think about it, eta tends to infinity. So eta tends to infinity as n tends to infinity. I mean, if n's very, very large, eta is going to tend to 1. You can see that quite easily. Okay, so this number is going to approach this number here, n. So just to illustrate matters once again, I've got space here, number of stages, hardware stages, and time. When you start the pipeline up, you're going to have idle periods. Here's task 1 plus task 1 plus task 2, task 1, 2, and 3, and so on. And at this point, I've still got a couple of things to run. I'm not putting any more tasks into the pipeline here or here or here. So these are all idle space-time spans. So throughput, and the idea is that it's inefficient. It's a very inefficient use of the pipeline if n is small. So I'm just going to give you one final definition you'll be glad to hear of throughput. Okay, so definition, 5th definition I've given you. Throughput W is the number of tasks that can be completed per unit time. It's actually very easy. So you're wondering what the throughput is. It's the number of tasks that have completed divided by the time it takes to complete those n tasks, which is k times store plus n minus 1 times store, as we've seen already. This is the time it takes the pipeline to complete n tasks. And that actually simplifies to efficiency divided by tour. You can just check that, efficiency by tour. If you divide this expression by tour, you're going to get e to divided by tour. Okay, so throughput is the number of tasks that can be completed per unit time. I want to know how much work my machine is capable of doing. Now, what can it do? What can it accomplish per window of time? Right, so a little note on that. Okay, a little note on that. So here's a sort of a practical example. Here's a sort of worked example, nearly completely worked example. Suppose that a processor can execute any instruction by means of 6 basic operations. First of all, fetch the instruction, decode it, execute it, code, decode the address, memory access, and write back. And we didn't look at all these operations when we considered our simple architecture, but they're easy to understand, and each operation should take 1 clock period. And we'd have to, as designers of a CPU or processor system, we'd have to decide what a suitable clock period was, obviously. So the example requires you to use a space-time diagram to show how pipelining the hardware units responsible for the basic operations, those 6 operations, can lead to a speed up over an equivalent non-pipelined processor system if just 3 native instructions are executed. Right, so I want you to think about the possible speed up of using a pipeline to do all that. Right, so K-stage pipeline processes n tasks in time k plus n minus 1 clock periods. I don't perhaps need to explain it again. Same number of tasks executed in a non-pipeline processor with latency of t equals n times k clock periods. So the speed up is going to be t divided by tk. And just substituting for n and k here, we get the speed up of a 5-stage. Oh, it should be 6 actually. So I made a technical error here. So the speed up of a 6-stage pipeline is 3 times 6 divided by 6 plus 2 minus 1 equals whatever that happens to be. And it's going to be around about this figure. I mean, if I was operating with 5 stages rather than 5 operations instead of 6, as I've just actually set out, I'd get a speed up of 2.5 times. And in that case, if the pipeline is kept busy and n is very large, then the potential speed up of a 5-stage pipeline is 5. A speed up of 5. So have a think about that. And I mean, the question I can could ask you is, what exactly do you understand by the concept of speed up? What does it mean exactly? So, to summarise the presentation, pipeline parallelism um, is what we've been discussing. I mean, how it operates, what technical potential advantages that it has, the importance um, in building using factories and production lines and so on. And even the educational process itself is being industrialised, or was industrialised about, say, 10 years ago, in exactly the same way. I mean, somebody would actually write the module handbook or module materials. Somebody writes the lectures based on the module handbook. Somebody, or more than one person, according to specialism, gives the lectures and so on. And maybe another person does online assessment. You might have 10 people involved in the inexpensive and fast production of learning materials. So have a think about that. And I'll finish there. Okay, thank you very much.